My name is Dr. Vadim Keyser, and my research is on measurement theory in the physical and biological sciences. Measurement gives us information about the world. For example, the height of a plant, the age of a fossil, the physiological development of an organism, and even its extinction event, or the heat of the surface of the sun. But what is measurement? Early accounts of measurement theory focus on the systematic assignment of quantitative values, like a given numerical reading on a thermometer, to objects in the world, like the temperature of the surface of the sun. Newer theories of measurement focus on the selective representation in measurement. This is parallel to the scientific activity of modeling. Models and measurements selectively represent properties of systems, like structural properties. For example, measuring DNA requires selective, fine-grained preparatory procedures and instruments, like electron microscopes, which represent certain structural features by using different physical principles to create the output image. For example, by blasting the sample with high voltage electron beams to create the output. This is the transmission electron microscope. In my research, I focus on how the process of measurement works. I ask, how do we systematically account for the causal conditions in the total measurement process? Measuring is not just about representing. For example, when we measure the boiling point of water, we're not merely taking a final thermometer reading of some stable value of a quantity. Water boils at different temperatures depending on atmospheric pressure and the presence of dissolved gas. These are measurement conditions. So before we get to the final reading on a thermometer, we have to make certain conditions repeatable and reproducible so that we have a stable boiling point. The manipulation of causal conditions is relevant for many context-sensitive biological phenomena. Take the turtle. A turtle's sex is determined by the temperature it is exposed to during a certain stage in development called the thermosensitivity period. A currently unraveling problem in ecological developmental measurement is that when you measure developmental phenomena, such as the thermosensitivity period, in different measurement contexts, like the field, the lab, and computer simulations, you get different results. These measurement context-sensitive results even extend to differences in behavioral phenomena, like the speed of a turtle's flip-over response, called the writing response. Why should we care about solving such measurement problems of turtle dynamics? Because field, lab, and computer simulation measurements give us different predictions for what will happen to turtle populations during global warming. In my research, I also analyze how multiple measurement processes check each other's results. Take something as simple as multiple observers of a phenomenon. What can we conclude if those observations match? If some of them don't match? In my research, I present a theory of robust measurement, where we obtain information about error and reliability when we compare multiple independent measurement processes. Each process is layered with measurement condition setups. For example, preparatory procedures, variable manipulations, etc. There can be many layers as well as numerous measurement comparisons. Scientists use theoretical models, sometimes single models, sometimes multiple, sometimes partially dependent models, to characterize error. This is done by using diverging and converging results to locate where error occurs in the measurement process and how it operates. Let's simplify the scenario to sensory modes of measurement. Suppose you're seeing a shoe floating on the street. You can't believe your eyes. Potentially others near you are making the same observation, but then you extend your really long arm to touch it and there's no space underneath. Your two measurement modes don't match up. You could even introduce a third mode where you reflect sound waves off of an object like a superhero. Touch and sound agree, but they disagree with observation. Theory steps in to characterize why the visual measures are getting different results than the other modes. One theoretical explanation is that we're dealing with a mirage, in which light rays produce a displaced image. Light refraction would not affect the other modes. The divergence and convergence in results is explained. But something that should trouble us in this example is, if you go deep enough into the processing layers of each sensory mode, you see that they're all connected by a single processing system, the brain, which means the modes are dependent. This could potentially compromise the cross-checking mechanism. To see why, The nature of independence in measurement requires careful analysis. In my research, I focus on the independence of measurement processes to solve epistemological problems like, how do we differentiate robust results from pseudo-robust results? For example, when physicists recorded results that neutrinos traveled 60.7 nanoseconds faster than the speed of light, there weren't just a few trials, but 15,000 trials that supported this result. However, the result was not robust because each trial was dependent. In fact, a simple error compromised the result of each trial. It was discovered that the 60 nanosecond discrepancy came from a poor connection between a fiber optic cable that connects the GPS receiver used to correct the timing of the neutrino's flight with an electronic card in a computer. All 15,000 trials were polluted by this error. I apply my theory to complex forms of measurement. For example, climate science. Understanding climate change requires looking at physical measures, like radiosonde and satellite measurements, but it also requires running computer simulations called models, which are simulated climate systems. I'm interested in questions like, what can we conclude when physical modes of measurement are dependent on a background assumption? Is robustness compromised if models share design elements, for example, initial conditions and parameterizations? How do we systematically compare physical measures to computer models? And in what way does theory mediate these comparisons? In my research, I answer these questions by analyzing the relations between computer simulation models, physical measures, and theory. My research aim is to use my theory of measurement to solve measurement puzzles and to systematically answer questions about measurement practice in the physical and biological sciences. Thanks for listening.